So welcome back, everyone. I hope everybody had enough time to get some food or is fine waiting until a little bit later. We're going to recommence the first day, Algorithms Day of the Summit now with a set of really wonderful keynote talks. And we've been thinking about open problems in various ways. This morning we were thinking about the open-endedness problem, general intelligence, what kind of cognitive biases can we learn from studying human gameplay. And this afternoon, we've got a very interesting set of open problems too. If I were to find a theme amongst the first few, it's the idea of data efficiency. So on one hand, we've all heard about and probably experienced the sort of radical improvements in AI capabilities through training these extremely large, highly parameterized models on a vast amount of data. And we've seen many successes to this. We know these models have many failure modes too. And as a cognitive scientist, I also like to think about how human cognition is good, not when n goes to infinity, the number of samples, but when n goes to 0. How do we act in the small sample regime in a way that generalizes well, and in a way that doesn't have some of these failure modes? So first, we're going to hear from Dr. Martin Riedmiller, who is a research director at Google DeepMind and the lead of the control team. We also, before lunch, we were talking about this theme of the sort of modern academic journey in AI through perhaps academia, industry, nonprofit, trying to make sense of that as young researchers. And so I think Martin is one of the few people I know who stepped down from being a professor of machine learning to go on then and lead a team at a tech company. And I think through his talk, we're going to see maybe directly or maybe indirectly some of the benefits from doing so, being able to work with a lot of compute and large models. And in a different kind of work and research environment. So today, Martin is going to talk about why data-efficient reinforcement learning is crucial to the larger problem of artificial intelligence. We're very fortunate to have him today. If you'd join me in welcoming him to the stage.
Thank you. So thank you very much for this kind introduction, and thank you for inviting me. Welcome, everybody. With respect to the open problems in AI, I'm particularly focused on data-efficient reinforcement learning, and the talk I will give you hopefully some good arguments why this is important to finally solve AI. And this was work done with all these fantastic colleagues at DeepMind, so I want to thank them too. When going back to the very first proposal of artificial intelligence, the Dartmouth proposal, which I like a lot, it was very ambitious, and the study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle so precisely described that a machine can be made to simulate it. And this is a very bold statement and a very bold mission, which we are still on with this current hype in AI. So every aspect really means every aspect, not only the higher cognitive level, as it is currently popular with the language models, but also the sensory motor level, the very primitive levels, where directly experience kind of is transformed in reasonable control signals of a very rich body that starts with a baby that is just exploring the world and then ends up with highly capable humans that are doing all kinds of very cool stuff, like downhill mountain biking, whether I always have arguments with my wife whether this is truly intelligent behavior or not. So there are a lot of desiderata for this low-level sensory motor control that we want to learn. First of all, it's really based on self-learning from own experience. So there's not a book that the baby reads and then understands how to deal with the body, but it's really a direct interaction with the world. It has to be highly data efficient because lifetime is precious. And on the other side, it also has to be open-ended because there are so many tasks that can be done with a human body and so many challenges. And that is the way how we interact with the world. So you don't want to rely on a certain knowledge that you have pre-built, but you really want to have something that is, in principle, able to do everything that is possible with your body. And if we want to transfer this to an artificial system, to a research program that I called Artificial General Control Intelligence, then we have two main things. One is that we want to have minimal prior domain knowledge. So we don't want to be in the state where for every new task we have a lot of human engineering brought into the process in order to reduce the bias that we bring in as human engineers. We have a certain solution in mind, but also to enforce this open-endedness. And the other thing is then if you want to do reinforcement learning from experience only, you also want to make sure that you're really data efficient, because if you want to apply this to a robot, then every interaction with the real world is really precious. That costs you a lot with respect of actually experiment time. And ideally, you want to be at least as fast as the human learning things. And we know that it's possible in principle because we have this example as a human. So we are now interested to kind of bring this into an artificial system and understand the principles behind it. So for us, it's okay to bring in some general structure into the controller or to use generally available data. That is absolutely fine. What we ideally want to avoid is that we rely on task-specific human intervention. So for example, writing sophisticated simulators so that the sim-to-real transfer works, or giving demonstrations to the system. Ideally, we really want to stick to the pure self-learning paradigm. And if we're successful, then we not only make probably a step to understanding a bit more of this wonderful intelligence that we see in human, but also this has a potential huge practical impact. Robotics is one, but in general, the world of control system, of closed loop control, is based on these principles. And in general, we would know, or we have some ideas of how to approach this based on the work of Sutton and Bartow, Bertsekas, Watkins. It can be formulated, the control problem that we have can be formulated as a reinforcement learning control problem, where we try to optimize the reward that we get over time that perfectly fits to this closed loop control. And if we formulate, for example, we have very simple formulation. If the system achieved the goal, we get a reward of 0. And if it's not quite at the goal, then we always get a reward of -1. Then we have a very simple formulation of what we want to have. And then the system has to solve basically this optimization problem. And also there's a bunch of work how to actually tackle this optimization problem by dynamic programming methods, which lie the ground of all that. And then learning a value function, either model-based, a true value function, or a Q function that depends also on the action, by iterating through these experience and updating these value functions. And there also have been big successes, like applying this method. AlphaZero for chess or for learning Go was one of these breakthroughs where the system actually learned from scratch to play Go or chess on a master level. For chess, it only finally needed 4 hours to get on a master level of chess, which I still find very astonishing. But this basic framework requires a lot of data, tons of data. And this is fine in these board game scenarios because you can simulate a lot of board games, and so you can just always generate the data. But this is probably not fine if you want to have the control of a robot where every experience is more costly. And so one simple but very important idea was not to throw away the data, but really use this experience, the observation, the action, and the next state or the next observation, and always iterate through it. Because this is basically reflecting just how the world behaves, and so this is also true after some time. And the neural fitted Q algorithms, or the fitted Q framework from Ernst, they were independently invented at about the same time, and they helped to actually make this breakthrough to make the reinforcement learning highly data efficient. And there were a lot of variants developed finally after this idea of storing the data, and they are still used today. Whenever it comes to that data efficiency is important, an important feature. So here are some examples, and all of these examples are learned from scratch, so there's no simulation involved. They are directly learned when applied to the system. Cart-pull system, that was one of the first reinforcement learning benchmarks, basically the Drosophila of reinforcement learning. And this is here learned directly on this device in less than 300 episodes without having to go through all the modeling that classical control theory has to do. A similar thing was done in learning to steer this car. And as you see, in the beginning of the learning, it wiggles around very much. So one of the engineers said this is probably the first time that a car will fall over at 10 kilometers per hour because it brought so much dynamics into the system. We applied it in RoboCap to actually learn a dribbling routine that was much more efficient than everything the student did come up in years of prior work to that. And with that, we won the World Championship in 2007. And we even had a very first deep reinforcement learning system running in 2009, where directly we used raw pixels from a camera to steer a slot car. And all that learned directly by interacting with the device, where data has to be used very wisely. And our current research is still ongoing in this effort to make it more and more data efficient. And our leading motto is data is precious and data is true. Therefore, we really want to squeeze out as much as possible. And that finally leads us to this paradigm or this viewpoint that basically if we want to do data efficient reinforcement learning, then there are two crucial processes. One is if you have given a data set, so you assume that you already have a collection of data, then find the best algorithm that gets out the best knowledge possible out of that. And this seems kind of trivial, but we will see that this is a research topic, and the more you can advance in that, the better your final system, the more data efficient your final system will be. And then the dual part of that is collecting the data, which is understanding which data is actually needed to maximally increase knowledge. And this is deliberately different from the classical reinforcement learning paradigm, where you usually use the current best policy and apply a bit of random sampling around that to get an idea. This is clearly says, no, there are probably better methods out there to collect the data if you understand what data is useful in order to boost your current performance. And around this paradigm, over time, we developed this architecture, which is based on the so-called agent state, which consists of the raw experience, that is the interaction data that we have collected with interacting with the real world, all this observation, action, next observation, all these triples. And then the knowledge that is generated out of it. So the classical way would be to generate, be the policy, the only knowledge. But since we want to be more general, we also allow, for example, from the same knowledge for example, to derive a model in order to do some planning, or to derive even novel rewards by some curiosity principles, or to derive observers that maps the observation to a different state representation, which is probably generalizes better. So really think of that as a couple of inference processes that asynchronously work to get knowledge out of the data. And that is one of the crucial feature of this architecture. And then on the left-hand side, we have the collection process, which then takes all the knowledge and understands, okay, this is my current state of knowledge. What should I do next in order for increasing the knowledge in the next step the most? So basically, our research centers around these questions, and also understanding the interaction of these processes in order to get better and better agents that are more and more powerful and understand the world better and better. In the following, I will give you some examples of the methods that we are developing and how they help to improve data efficiency. And then I will also give you some examples of how this is actually applied in the real world nowadays. So the first part is the inference part, doing better inference. That is the case where we have given a set of experience, the upper circle over here, And then we take the data and try to get out, for example, a better policy. And we have developed a couple of algorithms, and one I want to go a bit more into details. For example, the data that you have available could come in completely different forms. So data could be that someone has already shown you how to solve the task, and then you could probably get along with just doing supervised learning. But data could also be much more messy, so just being randomly collected. And then we know that if the state space is kind of explored efficiently enough or rich enough, then Q-learning might do a good job. And our batch reinforcement learning algorithm called DIME that tries now to balance between these two facts if we don't know what the data actually looks like. So there's a parameter alpha now that can be used to adapt the performance depending on whether the data is more noisy or more can be used for supervised learning. And this alpha kind of is a mediator between these two extremes. And with one learning run, we can now derive a policy that is conditioned on that parameter alpha. And by playing around with this alpha, we could find the policy that works best, that takes the best out of the data sample that we were actually given. And to show you that this is really important and this has an effect, here's a table that we derived from that. So here are a couple of benchmarks where data has been collected in various forms. And then you see a couple of batch reinforcement algorithms. And the higher the number, the better the algorithm actually achieves. So the better the performance of the final policy is. Or the better the performance of the final policy is, and you see that the performance of the algorithms varies a lot. So the same data set, it's only the algorithms, and the algorithm is that we can influence without interacting with the system. So that doesn't cost us anything with respect to data sampling. With choosing the right algorithm actually has a huge impact on the performance that the system can get out. So it's important to do research on that front of things. The complementary way is to collect data, and there we also think about what can be good ways to do better exploration beyond just epsilon greedy, where you add random noise to your current policy. And we came up with different frameworks, which I will SecX and SSIs, I will explain a bit more in the details. We were also kind of investigating a bit more in curiosity-based algorithms where the system actually is looking for finding novel behaviors just out of very basic principles to master new systems. So the idea of this scheduled auxiliary control is very much inspired by these babies, by learning, by playing. And the main key ideas are that these transitions and rewards can be separated. So not every transition comes with a reward, but for every transition you can basically have multiple rewards. And you can learn them in parallel, and every policy that results of that then tries to optimize the reward that you are attaching to that particular triple of experience. And of course, this makes learning much more efficient because every observation that you make can not only be used once, but could use multiple times in multiple iterations, and can be used also to learn different policies at the same time. And the second thing is that complex tasks can be achieved by sequencing simple tasks. So if you can kind of interact with the world and do simple things, and you do a couple of these simple things, then probably much more complicated behavior just emerges just out of the sequence of this. And with these principles in mind, we built an algorithm. I don't want to go in the details, but it's very much like collecting the data, then annotating the data with different reward settings. The rewards are very simple, and then using a sequence of these simple policies that have been derived to get to more and more complex behavior in state space. I want to give you one example. So for robotic manipulation, if you have a 7-degree robot arm, then controlling it in a reasonable way is pretty complicated, because you can imagine you can turn and actuate every joint. So there are a lot of degrees of freedom that you can do, and it's not obvious how to actually, by random exploration, how to do something reasonable. What we do in this scheduled auxiliary framework, we have a couple of rewards that we define, which are just come out of some insights in the domain and the sensors that you have. So, for example, reaching an object is a reasonable thing, or touching an object because you can sense it with a sensor in your fingers, for example. Pushing an object because then an object moves. Lifting an object can be something, opening, closing the fingers. So there are a bunch of rewards, which we call usually a book of rewards, that are defined. And the benefit or the interesting thing here is that they are very simple to define. And there's also no explicit curriculum involved in that. So it's just a reasonable thing that you would do in such an environment. And then we expect our algorithm to learn a curriculum, an autonomous curriculum, from simple to complex. So here you see an example of a Jaco robot arm. First in simulation, I will also show you some real robot experiments. And if it's untrained, it just does some random movements. And with some of those random movements, it actually touches, for example, the table or sometimes the box. And then it gets a first reward. And then this policy starts to get better and better. So one of the first things that it randomly can discover is that touching something is possible. And then we can have a policy that actually deliberately touches something. And then it can also, when it touches something, then you also see that it moves. So the second auxiliary reward, like moving things, also starts to develop a policy so that you can arbitrarily move or deliberately move things. And then when you move things, then you're also interacting with that. And then if you, at the same time, for example, by chance, closing your fingers, then you also can get your first lift reward for something. So very much in analogy to the baby that we saw before. And then we can actually learn to put things left and right once this lifting policy has gotten some signals. And then we can also learn to stack objects. And finally, what we wanted to do is actually to clean the table, because we know that is also very difficult for children. So we wanted to see whether the robot finally can learn this. And with this, all these simple auxiliary rewards, it finally discovered the behavior in this rich space, so that it was actually able to put these objects in the box, opening the lid and putting the objects there. And the same kind of agent, also the same kind of software, the same kind of brain also works for different robot arms. So if we now replace the grippers by fingers, in principle the same agent would do the job. So with the current advent of LLMs, of course, we are also looking what we can do. And we in particular think that it's very interesting to bring some real-world knowledge into these agents. So we still have this low level with this collect and infer loop, but we're now using these LLMs as a kind of backbone to bring in some knowledge. And one example of this was done by some work of a student researcher in my team. Here is with the example of learning to triple stack, and you can imagine that is pretty difficult to achieve. So the only thing that you get finally from the environment is when you achieve the triple stack, and then we can ask an LLM, give me some intermediate steps or sub-goals plans for what should I do to stack all three objects, and then the LLM answers with some intermediate steps. For example, the robot is grasping the green object. The green object is on top on blue, and then with an additional VLM, we can check how the description of what the sub-goals that the LLM provided kind of align with that what's actually seen in the image. And by this, we now also can generate much more rewards. So there are more intermediate rewards and not just the final rewards. And we also have the possibility to say, okay, I'm now able to stack the green object on the blue object. That part already works, so I don't have to work on this again. The crucial part is now to bring the red object to the green object. So I can really focus my data collection on that last part, if I understand this correctly. And therefore also, again, reduce data or improve data efficiency by now having some task understanding that's brought into this world of reinforcement learning. Here's an example, learning curve without any structure. This wouldn't be possible. It wouldn't observe. And with more structure, then the learning curve gets up much earlier. And the last part of my talk, I just want to show a couple of real-world examples. One of a highly dynamic system, bringing a ball in a cup, and this has been solved by for example, by Jan Peters' group a couple of years ago by kinesthetic teaching. So there was actually a human kind of controlling the robot and then trying to bring the ball in the cup. And then it was basically copied by the system. And we wanted to go another way, to just say, okay, now we just have the situation like a baby. So we get the raw pixels as input. And we only get the signal once the ball is in the cup. And then the robot has to learn actually how to do this movement. And the rewards that we give is whenever we want to observe some movement in the scene. So we want to see that something is happening, like basically some curiosity reward, like a baby would probably do. And finally, after 5 days of learning, learned a highly dynamic behavior, and of course there's also some noise involved, so it's not only always the same movement, but it actually depends where the ball is flying and catches it. And this is just from the raw stream of 2 cameras and these very simple reward signals, which would probably be a mess to do this in a classical way. We also applied this to locomotion, where we set up one single brain with one set of rewards, very simple rewards, so like using the IMU to detect some movement. And in all of these cases, the learning time was less than 24 hours in real time. So in simulation, we were able to have more different architectures. So you see the policies look very different. The reward that the agent gets is always the same. So it gets reward for moving forward. And for this hexapod, the movement is completely different from this 2-leg walking machine, because in 2-leg walking, you also have to learn to balance. But the system finally figures out that a different physical system comes up with a different policy, but the brain itself is constructed in the very same way. And we could even put some roller skates down there, and it learned to learn a roller skate movement. And on the left-hand side, you see some experiments that we did on a real robot, and it was very fascinating to see how quickly it actually learned to move forward. This only took about 100 to 120 trials, which is about 3 to 4 hours. And then some final benchmark, again in manipulation. We had proposed a benchmark for stacking, but not only stacking 2 cubes, but to stack different shapes, because then the robot or the brain, the agent also has to learn the physical behavior of the different shapes, making the problem much more complicated. And we try to solve it with classical sim-to-real approaches and careful design of rewards, and then zero-shot sim-to-real to the real world, and got about 80%. And then we said, why not trying it directly, end-to-end learning on robots directly? We used 10 robots, 1.5 months, which overall is 15 months of learning time, so a quite reasonable time. And we're using our approaches. And here you see some of the stacking challenges that you actually have. So the surfaces are not always flat. or you need to do some balancing if the shape is different, or it's difficult. You have to have the right angle for grasping the object, and all that the agent has to understand in order to be successful. And this is the final results. You see, it solved the problem by nudging the lower object until the surface is in the right position. And it has to do this very carefully, because if it forces it too strongly, then it is punished, because we don't want the robot to break. And it also solves the other challenges. And the nice thing is that also the movement, if you notice, this is very smooth and very goal-directed. Okay, and with that, I'm at my summary. I hope to convince you a little bit that self-improvement and data efficiency are core features of intelligence, at least of intelligence if we understand this in the original sense, that we want to understand all aspects of human intelligence. We made significant progress in data efficiency, in increasing the complexity of the tasks. The number of action dimensions here plays an important role. The horizon of when you get reward plays an important role. We are able to learn from raw pixels. That is also something that was not imaginable 20 years ago. And we are working towards increasing autonomy. And in our work, there's a broad spectrum from practical relevance. So we also apply this to control fusion reactors. So something that really manifests also in the real world at some times, hopefully, to understanding intelligence as this low-level control, as one building block of a true AI that understands from the low level to the high levels, all what humans are able to do in the real world. And to conclude, I want to the one-sentence summary I want to give is we have not achieved AI unless we got the human out of a loop, and that's what we are trying to work on with my team. Thank you.
So, Martin, thank you very much for that fascinating talk. Do we have any questions for Martin from the audience? So there's one hand straight up there from Greg. If we could run him a microphone.
It feels like there's an aesthetic to curiosity, a kind of feeling that things are unusual, surprising, but satisfying at the same time. Is there any way in which you could create your own fun, curious goals, where the robot's like, I wonder if I could do this, or wouldn't it be cool if all the blocks were stacked on top of one another? And that would feel satisfying or surprising, and then that would enable it to explore interesting parts of the space that will perhaps be useful for other tasks.
Yeah. The answer to that question, I would be really interested too. So the level of curiosity that we are working currently is at least to avoid redundant data collection. So for example, to get stuck to over and over do the same thing that we already know and have a sense, okay, here I'm already good. And then curiosity is very often like similar to predictability. I know, oh, I did it, I did this, I know what happens, so this is boring, let's get to something else. And this is probably the lowest level of curiosity. What you are describing, like also understanding, I'm doing this because this is now really cool and I understand what cool is, that is a very interesting question, and we have discussed this and have some, at least we observed some interesting behavior that emerged from that. But how to actually judge that this is more interesting than the other? We only have some initial guesses. Like for example, if it's in a physical simulator, if this situation would be more unstable than another, that is probably an indication that if you can still achieve this. Then this is probably cool. An example would be if you balance the pole like this, not cool. If you balance it like this, cool, because it's more difficult, obviously.
And David?
Okay, thanks. Actually, it's related to the last question. So when we learn as babies, and you have that whole thing, there's play, and then you learn stuff. And then we go to school and we get taught science and scientific method. And science is in some sense directed play, in the sense that you interact with the world, but you do so in a way to remove confounders and to, you know, have a structure to the play. Do you imagine you could do something similar where you reward the type of play that will be more scientific, so that we do experiments that then allow us to learn about the world with much less data because we've controlled the thing?
I think that's also a very good question. And I deeply believe that the principles are very much the same for doing interesting stuff in science than doing interesting stuff for the baby. I would be very much fascinated if we find something that says, okay, we can really start from scratch and applying the same principles, but if we apply this at a different scale and with a different set of knowledge, we will discover exactly and go in these directions. But the principles that are behind it, they do not change from level to level. Because at some point, if you think of it, the brain, it's chemical processes, physical processes, and probably there are not for every situation, there are different processes at the end.
I might pick up on that and use my kind of right as summit chair. So when you think about a lot of scientific discoveries, it seems to come from both consideration of the data, but also the model, you know, explicit consideration of what the constraints of the model are, what its scope in terms of data is, and maybe comparison with another model. In your infer and collect framework, do you see evidence for that? Is there room for it?
Yeah, I think in principle, there would be, because the experience that we have is like also the humans are when they are born, they come to the world basically blank with some things built in, some mechanisms built in by evolution, and then the rest is using this experience to continue. And I think, of course, this agent that we're currently proposing, with all the experience being there and just stored and being revisable, that is probably not the true answer, because there's probably this would be too much of a demand for a brain. So this process that kind of condenses this in more information that is then probably not so true anymore, but still related to the original experience. This will probably help us then to scale and then not always to work on this raw experience, but then treat this condensed experience as the raw experience of the next level.
Oh, thank you. So we have time for one more question. I see one more just down here. It'd be nice to hear from a woman, if we could. Yeah. So there was one right in front. Yeah.
Do you work on robotics because you believe the applications are interesting, or do you believe like AI needs an embodied component in order to achieve like a more general intelligence? And what do you think are like promising avenues to generalize or like to bridge the gap between like more cognitive, like lingual forms of intelligence and like physical intelligence?
Yeah, that's also a very good and even a personal question, because when I started with all that business, there was a lot of discussion also of embodiment, how important it is to AI, but at that time it was really kind of blue sky discussions, because we didn't know even how to build the simplest system and didn't have language models that we have now, where we know that there are different cognitive levels that we can probably build with artificial systems. So I originally started to do robotics because I wanted to focus us on this data efficiency aspect. And if you're doing real-world robotics, you cannot cheat. If you're doing simulation, you can always say, this is probably balancing this pole is too difficult. Why don't I make it a bit longer, or why don't I change the mass a bit? Oh, then it's probably out of a sudden it's getting easier. Or I do a bit of a different simulation that looks good in simulation, but is not quite the real world. If you're doing real robotics, then you cannot cheat, and you really have to. Data efficiency hurts. So if an experience runs 12 years instead of 12 days, this is for an impatient scientist, this is completely a game changer. So I originally started this, the robotics, because I wanted to focus on data efficiency. But now I also think with these language models that are learning purely from, they are always using this human in the loop. We all compile this knowledge into some form that obviously helps to generalize these language models in a very profitable way. But all the hard work was done by humans to bring it actually into language. And so I think more and more probably there is no way, if we want to understand AI, the principles of AI and in the sense of how they scale and how it all connects together, we probably need this embodiment and understand at least what this means to get from raw experiments to some compiled form, and what is the mechanism that triggers us to do so.
Thank you. It's genuinely fascinating.
And that's all the time we have for questions. So can we thank Martin again for a wonderful talk? Thank you, Martin.